In the last tutorial, we discovered that there are two major subfields within unsupervised machine learning: clustering and dimensionality reduction. We're already familiar with clustering, so what is dimensionality reduction? According to the Wikipedia article on dimensionality reduction is the transformation of data from a high-dimensional space into a low-dimensional space, so that the low-dimensional representation retains some meaningful properties of the original data. So, what does that even mean? And what is principal component analysis? And what does it have to do with dimensionality reduction? Well, let's find out. Welcome to Julia for Talented Amateurs, where I make wholesome Julia tutorials for talented amateurs everywhere. I am your host, the Dabbling Doggo.
I dabble.
With the exception of the MNIST datasets, all of the datasets that I've used on this channel have been relatively small datasets with only a few features. Now, what happens if you encounter a large dataset with thousands of features? Trying to work with such a large dataset may be unmanageable for both humans and for computers. What if there was a way to reduce the number of features, but without losing all of that information? For example, what if you could go from thousands of features to just 100 features that retained most of the information from the original dataset? That's the idea behind dimensionality reduction. Despite its less than catchy name, dimensionality reduction is extremely useful and has many practical real-world applications, like data compression, signal processing, speech recognition, neuroinformatics, and bioinformatics. It's commonly used as part of a data analysis workflow in order to clean up large datasets for use further downstream, whether it's for data visualization or for pre-processing input data for a machine learning algorithm. There are many different algorithms that fall under dimensionality reduction, one of which is called Principal Component Analysis, or PCA. PCA was invented in 1901 by Karl Pearson, who was an English mathematician and biostatistician. This is the same Pearson known for the Pearson's chi-square test. As a side note, despite his many contributions to the field of mathematical statistics, he held some questionable personal views that would be considered quite controversial today. In any event, here's the idea behind PCA. Let's take the IRIS dataset as a motivating example. The IRIS dataset is difficult to visualize since it has 4 features, and you can only plot a maximum of 3 dimensions. So, if you had to pick 3 features, which ones would they be? And if you leave one out, then you're missing some information. So any 3D plot that you generate will not be an accurate representation of the entire dataset. Now, what if there was a way to reduce those 4 features into 3 features? Not by deleting a feature, but by compressing that data to generate a new dataset with only 3 features that retained most of the information from the original datasets. That would be useful, right? Then you could use that new compressed dataset to generate a 3D plot that was an accurate representation of the original datasets. That's the idea behind PCA. PCA is a method of compressing your data while retaining the most important information from your original data. The result is an abstraction of the original dataset in a much more compact and manageable form. Let's go through some code to help illustrate the concepts behind PCA. For this tutorial, knowledge of Julia and VS Code is required. I'm also assuming that you're watching this entire machine learning playlist. In your VS Code Explorer panel, create a new folder for this tutorial. In the tutorial folder, create a new file called ul_pca.jl. Launch the Julia REPL by using Alt-J, then Alt-O. For this tutorial, I'm going to dock the REPL panel in the same panel as my editor. In the REPL, change the present working directory to your tutorial directory. Enter the package REPL by hitting the closing square bracket. Activate your tutorial directory. Add the following packages: multivariate stats, plotly.js, plots, and R datasets. Type in status to confirm the version numbers. Exit the package REPL by hitting backspace. Okay, let's get started. Let's start by loading some packages. The multivariate stats package is a statistics package that contains a lot of useful statistics algorithms, one of which is the PCA algorithm. Next, let's generate some random data. Using a random seed is not required. I'm using it so I can reproduce my results. Now that we have some random data, let's plot it to see what it looks like. For this tutorial, I'm using the Plotly.js backend to the plots package. The Plotly.js backend is a little buggy in VS Code, so I don't normally recommend using it. But Plotly.js does have interactive 3D plotting capabilities, so that's why I'm using it in this tutorial. Let's say this is our two-feature dataset. We're going to use PCA to compress this data into a one-feature dataset, while still retaining most of the information. Let's see how to do that. Like many machine learning models, the PCA algorithm requires the input data to be in a horizontal format rather than vertical, meaning that each row is a feature and each column is a sample. And like other unsupervised learning algorithms, PCA only accepts input data and no output data. That last argument is short for maximum output dimension. By using a value of 1, we're saying that we want to compress our datasets from 2 features to 1 feature. If you look in the REPL, you'll see the output from the model. That top line shows that the model took 2 dimensions in and returned 1 dimension out. The principal ratio, with a value of roughly 98%, means that the PCA algorithm was able to compress our data from 2 features to 1 feature and still retain roughly 98% of the information from the original datasets. PC1 stands for Principal Component 1. What the PCA algorithm does is it takes your multi-feature dataset and then compresses it into something called a principal component. You can think of the principal component as an abstraction of the original features in a much more compressed form. There are a lot of other numbers here, which I won't go into. The most important things are to understand what a principal component is and to see how much of the original information has been retained. I know that's pretty abstract, so let's generate a plot and take a look at this principal component. You can use the transform function to generate the values of the principal component. The transform function is not to be confused with the transpose function. The transform function returns data in a horizontal format, which we will need to transpose before we can plot it. This is the plot of principal component 1. PC1 is a one-dimensional abstraction of our original two-dimensional dataset. Just like our original dataset, PC1 has 100 samples, but they're all plotted along the x-axis. Also note that the scale is different. The range has been normalized with a mean of 0. So now that we've gone from 2 dimensions down to 1 dimension, you might be wondering, is it possible to go from 1 dimension back to 2 dimensions? You'll be happy to know that the answer is yes. You can reconstruct your 2-dimensional data by using the reconstruct function. This reconstructed data is also in a horizontal format. The first row is an abstraction of feature 1, and the second row is an abstraction of feature 2. So, what are we looking at? The blue markers indicate the original 2-feature dataset. Those red markers indicate the compressed data generated by the PCA model. It's a little difficult to tell, but there are 100 blue markers, and there are 100 red markers. As you can see, the red markers are not the same as the original data. Instead, the red markers represent an abstraction of the original data that retains roughly 98% of the information. Note also that the scales for both the x and y axes are the original values. At first glance, the red markers may appear to be a linear regression line, but it isn't. Linear regression is interested in the relationship between an input and an output, so it measures the distance along the output axis, or y-axis, which is the vertical distance between a sample and the linear regression line. If you zoom in on the plot, you'll see what this plot is doing. For every blue marker, there's a corresponding red marker. The distance between the blue marker and the red marker is measured along a line that is orthogonal, or at a right angle, to the line that defines the red markers. The objective of the PCA algorithm is to find that line which minimizes the sum of squares distances between the blue markers and the red markers. You can think of the red markers as a projection of the blue markers from a higher dimensional space onto a lower dimensional surface. In this example, we're going from 2 dimensions down to 1 dimension, but you can apply this concept to any number of dimensions. Now that we have a foundation of the PCA concepts, let's save our plot and then move on to an application of PCA. Just as a side note, the Plotly.js backend doesn't save your custom aspect ratio, nor does it save any interactive features. So Plotly.js is useful for exploratory purposes, but it's not so great for presentation purposes. In this section, we're going to apply PCA to the iris dataset in order to reduce this 4-dimensional dataset into a 3-dimensional dataset so that we can generate a 3-dimensional interactive plot. As a reminder, we need to format our input data horizontally. The PCA algorithm does not require labels, so the model doesn't need an output vector, but we need it for plotting purposes. We also need the names of the unique species for plotting purposes as well. Next, we generate our model to reduce the dimensions from 4 to 3. Okay, let's pause right here and take a look at the REPL. The first thing to notice is that this PCA algorithm was able to reduce the iris dataset from 4 features down to 3 features and still retain roughly 99.5% of the information. This time, there are 3 principal components: PC1, PC2, and PC3. The principal components are sorted from most important to least important. The actual values shown in the pattern matrix are not important right now. What's important is the relative size of those values. Notice that the values in PC1 are generally larger than the values in PC2. Likewise, the values in PC2 are generally larger than the values in PC3. The values in the pattern matrix are the so-called loadings or weights. Each row in the pattern matrix is the weight from the original 4 features that have been assigned to the principal components. I realize that this is a confusing looking table with a lot of numbers, but the key takeaway here is that PCA is not actually deleting any of the original 4 features. Instead, it's projecting the values of the 4 features down into a 3-dimensional space, represented by these 3 principal components. The bottom section, titled Importance of Components, shows how much of the information from the original dataset has been retained by each of the principal components. This is another confusing table, but there are only a few important numbers to look at. Look at the second row called Variance Explained. This row shows that PC1 alone retained roughly 92% of the information from the original dataset. PC2 retained an additional 5%, and PC3 retained an additional 2%. So in total, PC1, PC2, and PC3 retained roughly 99.5% of the information from the original dataset, which is pretty amazing. As amazing as that might be, staring at a bunch of numbers is not as fun as looking at a plot, so let's move on. Before we can generate our plot, we need to use the transform function to generate the data for our plot. The result is a 3x150 matrix, with each row being one of the principal components. Notice that this new transformed data contains 150 samples, which is the same as the original iris dataset. We can now generate our plot. I'm going to use a slightly wider aspect ratio for this plot. What you're looking at is a 3D scatter plot of the iris dataset. It's not 3 of the 4 features of the iris dataset. It's all 4 features that have been projected down from a 4-dimensional space into a 3-dimensional space, which has retained roughly 99.5% of the original information. The blue markers are setosa, the orange markers are versicolor, and the green markers are virginica. Notice that the scale of PC1, PC2, and PC3 are all centered at 0. PC1 has the widest range, which indicates that it's contributing the most information. PC2 has a smaller range, and PC3 has the smallest range. You can rotate this plot by left-clicking and dragging the mouse. You can pan the plot side to side or up and down by right-clicking and dragging the mouse. You can zoom in or out by using the scroll wheel on the mouse. Finally, you can use all 3 to get the exact view that you're looking for. And if you ever get lost, you can click on the home icon to get you back to the default setting. Pretty cool, right? You can see a clear separation between the 3 different species. And again, you're not looking at 3 of the 4 features. You're actually seeing all 4 features, except that it's in 3-dimensional space. This is not the original iris dataset. It's an abstraction of the iris dataset that retains roughly 99.5% of the original information. Before we go, let's save our plot, and let's go through a recap of what we just saw. That was pretty interesting, right? So to recap, unsupervised machine learning has 2 primary subfields: clustering and dimensionality reduction. There are many different algorithms that fall under dimensionality reduction, and principal component analysis, or PCA, is one of them. The PCA algorithm projects data from a higher dimensional space onto a lower dimensional surface, while still retaining most of the information from the original data. PCA may be used for a variety of applications, including data compression and data visualization. Hopefully, you can see how using PCA might be useful, whether it's for machine learning or for some other purpose. Being able to compress your data while still retaining most of the information is a very important tool to have in your toolkit. The multivariate stats.jl package is not a machine learning package per se. It's primarily a statistics package that may be used with machine learning applications, among other things. The package contains a lot of different analytic tools that I did not cover today, so be sure to check it out. Unfortunately, I do not know who the original author is, but please be sure to show your appreciation to the developers and the contributors by going to the GitHub page of multivariatestats.jl and leaving them a star. Well, that's all for today. If you made it this far, congratulations! If you enjoyed this video and you feel like you learned something new, please give it a thumbs up. For more wholesome Julia tutorials, please be sure to subscribe and hit that bell. If you like what I do, then please consider joining and becoming a channel member. New tutorials are posted on Sundays/Mondays. Thanks for watching, and I'll see you in the next video.